You are bathed right now in the oldest light that has ever existed. It moves through walls, through skin, through the spaces between atoms. Invisible, everywhere, ancient. In 1965, 2 radio engineers in New Jersey found it by accident. A persistent hiss that no one could explain. That signal had been travelling for 13.8 billion years. It predates the first star ever to ignite. It predates the first galaxy ever to form. It predates the very ability of light to move freely through space. For decades, no one knew what it was telling us. Then 3 generations of satellites decoded its message. What they found was the age, the shape, and the composition of everything, written in microwave light. Tonight, we trace its discovery, decode its secrets, and confront the questions it still holds. If you are new here, subscribing genuinely helps. The oldest light has something to say. Let us listen. The horn antenna at Crawford Hill was never meant to listen to the universe. It was built for something far more mundane. In 1959, Bell Telephone Laboratories constructed a massive, oddly shaped receiver on a hilltop in Holmdel, New Jersey, designed to catch signals bounced off high-altitude balloons as part of Project Echo, an early experiment in satellite communication. The antenna was enormous. Its aluminium horn flared outward like the bell of some great instrument, 20 feet across at its opening, mounted on a rotating base that allowed it to sweep across the sky. It was, by any measure, a piece of Cold War telecommunications infrastructure. Functional, purpose-built, unremarkable in intent. But by the early 1960s, its original purpose had been overtaken by newer satellite technology, and Bell Labs offered the antenna for radio astronomy. 2 young physicists took it up. Arno Penzias and Robert Wilson were not looking for the origins of the universe. They wanted to measure the radio emissions from the halo of the Milky Way, and the Holmdel horn, with its unusual design, was exceptionally good at rejecting stray signals from the ground. It was in principle the cleanest radio receiver on Earth. They began their observations in 1964, and almost immediately something was wrong. No matter where they pointed the antenna, north, south, east, west, straight up, there was a faint, persistent hiss of microwave noise sitting in the data. It was not strong. It corresponded to an excess temperature of roughly 3.5 Kelvin, barely above absolute zero. But it would not go away. It did not change with direction. It did not change with the time of day. It did not change with the season. It was everywhere, all the time, coming from every part of the sky with precisely the same intensity. Penzias and Wilson assumed it was a fault. They checked every cable, every connection, every joint in the receiver. They rebuilt sections of the antenna's throat. They cooled the detector to eliminate thermal noise from the electronics themselves. They pointed the horn directly at New York City to see whether urban radio interference could account for the signal. It could not. They even discovered that a pair of pigeons had nested inside the horn and coated parts of it with droppings. They removed the birds, cleaned what they diplomatically referred to in their notes as a white dielectric material, and tested again. The hiss remained. It was not the cables. It was not the city. It was not the pigeons. It was not the antenna. It was not the atmosphere. It was not the earth. It was the sky itself. For months, the 2 physicists lived with a signal they could not explain. The frustration was real. This was not a dramatic quest. It was a quiet, grinding confrontation with a piece of data that refused to fit any known source. every explanation they could imagine had been tested and eliminated. What remained was something they did not yet have the framework to understand. They were hearing, though they did not know it, the afterglow of creation, the faint thermal echo of the moment, nearly 14 billion years earlier, when the universe first became transparent to light. The answer, as it turned out, was already waiting for them. It had been waiting for almost 2 decades. In 1948, a physicist named George Gamow, along with his colleagues Ralph Alpher and Robert Herman, had been working through the consequences of an idea that most of the scientific community still treated with skepticism: the idea that the universe had begun in an unimaginably hot, dense state and had been expanding and cooling ever since. If that picture was correct, Gamow reasoned, then the early universe would have been flooded with intense thermal radiation, and that radiation should not have simply disappeared, it should still be here. Cooled, stretched, faded, but still present, filling all of space as a faint thermal background. Alpha and Herman went further. They calculated what temperature that leftover radiation should have by now, after billions of years of cosmic expansion. Their estimate was roughly 5 Kelvin. It was a remarkably specific prediction, published clearly and without ambiguity, and it was remarkably close to what Penzias and Wilson would eventually measure. But the physics community of the late 1940s was not ready for it. The prediction slipped into the margins of cosmological thought and was, for all practical purposes, forgotten. The paper that had laid the theoretical groundwork was itself something of an oddity. Known as the Alpha-Beta-Gamma paper, it was authored by Alpha and Gamow, with the name of Hans Bethe inserted, largely as a joke, so the author list would read Alpha, Bethe, Gamow, an echo of the first 3 letters of the Greek alphabet. The paper's real subject was the formation of elements in the early universe, the process now known as Big Bang nucleosynthesis. But it was part of the broader theoretical architecture from which the prediction of leftover radiation emerged. A prediction that would take 17 years and a pair of confused radio engineers to confirm. By the early 1960s, entirely independently of Gamow's earlier work, Robert Dicker and Jim Peebles at Princeton University had arrived at the same conclusion through their own theoretical reasoning. They were not merely predicting the radiation, they were actively building a detector to find it, working out of a laboratory barely 60 kilometres from the Holmdel antenna. 2 groups, separated by less than an hour's drive, were converging on the same discovery from opposite directions. One armed with theory and purpose, the other armed with the most sensitive radio receiver in the world, and a signal they could not get rid of. The connection between them came through a chain of conversations. Peebles had mentioned the Princeton group's work at a seminar. Word reached Arno Penzias through a mutual contact. A phone call was made, and in that single conversation, the pieces fell into place. The hiss that had tormented Penzias and Wilson for months was not interference. It was not a malfunction. It was the very radiation that Dicker and Peebles had predicted, the cooled remnant of the Big Bang, filling the entire observable universe at a temperature just a few degrees above absolute zero. 2 papers were published side by side in the Astrophysical Journal in 1965. Penzias and Wilson reported their observation, carefully, modestly, describing only the excess antenna temperature and offering no cosmological interpretation. Deek, Peebles, Peter Roll, and David Wilkinson published the companion paper explaining what the signal meant. Together, the 2 papers changed the course of cosmology. The steady-state model of the universe, which had held that the cosmos was eternal and unchanging, suffered a blow from which it would never recover. The Big Bang had left a fingerprint, and it had been found not by a team searching for it, but by two engineers trying to make their antenna work properly. Penzias and Wilson received the Nobel Prize in Physics in 1978. Gamow had died a decade earlier, his prediction largely unacknowledged during his lifetime. Alpha and Hermann, who had published the specific temperature estimate that came closest to reality, received no Nobel recognition at all. Peebles would eventually receive the Nobel Prize in 2019, not for the cosmic microwave background prediction alone, but for a lifetime of contributions to physical cosmology that the cosmic microwave background had set into motion. The discovery had been accidental, the prediction had been forgotten, and the connection between them had come down to a phone call. And yet, what emerged from that improbable chain of events was nothing less than the foundation of modern cosmology. A single, measurable signal that carried within it the temperature, the age, and the story of the universe itself. To understand what Penzias and Wilson had actually detected, to truly grasp what that faint hiss of microwave radiation meant, requires travelling backward. Not to 1948, when Gamow and his colleagues made their prediction, but much further. Back past the formation of every galaxy, past the ignition of every star, past the first atoms, the first nuclei, the first moments of chemistry. Back to a time when the universe was something so alien, so fundamentally different from anything that exists today, that even the word universe barely applies. 380,000 years after the Big Bang, a span that sounds long in human terms, but is barely a breath in cosmic time, the universe was a place where light could not travel. That statement sounds paradoxical. Light, after all, is the fastest thing in existence. Nothing outruns it. But speed is not the issue. The issue is what happens when every path forward is blocked. In those first hundreds of thousands of years, the universe was not made of atoms. It was too hot. The temperatures in the earliest moments reached billions of Kelvin, and even as the cosmos expanded and cooled, it remained far too energetic for electrons to settle into orbit around protons. Instead, matter existed as a plasma, a seething, electrically charged soup of free electrons, bare protons, and helium nuclei, all immersed in an ocean of photons so dense that light and matter were effectively the same thing. Physicists call this the photon baryon plasma, and it filled the entire observable universe with no gaps, no voids, no structure of any kind. Within this plasma, photons could not travel freely. Every time a photon moved even a short distance, it collided with a free electron and scattered off in a random direction. The mean free path, the average distance a photon could travel before being deflected, was extraordinarily short. A photon might scatter billions of times before crossing even a fraction of a light year. The universe was, in the most literal sense, opaque. Not dark, far from it, but opaque in the way that the interior of a furnace is opaque. If you could somehow place your eye inside the early universe, you would see nothing but a blinding, featureless glow in every direction. There would be no depth, no distance, no horizon. Just light, trapped, bouncing endlessly between electrons, unable to show you anything beyond the plasma immediately in front of you. This is not a metaphor. The early universe genuinely behaved like a fog made not of water droplets, but of free electrons, and illuminated not by some external source, but by its own thermal energy. The radiation and the matter were locked together in what physicists call thermal equilibrium, each constantly exchanging energy with the other, neither able to decouple. The photons carried the temperature of the plasma, and the plasma carried the energy of the photons, and the two were so thoroughly entangled that distinguishing between them was almost meaningless. But the universe was expanding, and as it expanded, it cooled. This cooling was not dramatic. It was not a sudden plunge. It was the slow, relentless consequence of space itself stretching, diluting the energy of every particle and every photon within it. Over hundreds of thousands of years, the temperature dropped. From billions of Kelvin to millions. From millions to hundreds of thousands. Each threshold passing without fanfare. Each one bringing the plasma fractionally closer to a critical boundary that would change everything. That boundary arrived when the universe was approximately 380,000 years old, and the temperature had fallen to roughly 3,000 Kelvin. At that threshold, something quiet and extraordinary happened. The free electrons, which had spent the entire history of the universe careening through the plasma at tremendous speed, finally slowed enough to be captured by protons. One by one, across the entire universe, electrons fell into orbit around hydrogen nuclei. Neutral atoms formed for the first time. Physicists call this moment recombination, though the name is slightly misleading. The electrons and protons were not recombining, because they had never been combined before. They were meeting for the first time, but the name stuck, and what it describes is one of the most consequential transitions in the history of the cosmos. The effect on light was immediate and total. Neutral hydrogen atoms are, for the most part, transparent to the wavelengths of radiation that filled the early universe. The moment electrons were locked into atoms, the photons that had been scattering endlessly off free electrons were suddenly free themselves. The fog lifted. The universe, for the first time in its existence, became transparent. The photons released at that moment, the last photons to scatter off the plasma before it neutralized, have been travelling ever since. They were not emitted from a single point. They were released from everywhere, simultaneously, in every direction. The surface from which they last scattered is called the surface of last scattering, and it represents a kind of boundary, not a physical wall, but an observational one. It is the oldest light any instrument can ever detect using electromagnetic radiation. Everything beyond it, everything earlier, is hidden behind a wall of plasma that no photon from that era ever escaped. This is both a window and a wall. The cosmic microwave background is the deepest we can see into the past using light. It shows us the universe as it was at 380,000 years old in extraordinary detail. But it also marks the point beyond which the electromagnetic universe falls silent. Whatever happened before recombination, the processes that shaped the plasma, the fluctuations that seeded structure, the physics of the very first moments, can only be inferred. It cannot be seen, not with light. And after recombination came silence of a different kind. The universe was now transparent, but it was also dark. The plasma had cooled into neutral hydrogen gas, and no stars yet existed to illuminate it. The first generation of stars would not ignite for another 100 million years or more. This era, known as the Cosmic Dark Ages, was a universe filled with matter, but devoid of any new source of light. The only radiation present was the afterglow of recombination itself, still bright in the infrared, slowly cooling and stretching as space continued to expand. The cosmic microwave background is, in a sense, the last photograph taken before the lights went out. A portrait of the universe at the precise moment it became visible, captured in thermal radiation that has been travelling toward us ever since, stretched by the expansion of space from its original infrared glow into the faint microwave whisper that Penzias and Wilson would detect billions of years later, with a horn antenna in New Jersey that was never meant to hear it. In 1989, 24 years after Penzias and Wilson's discovery, NASA launched a satellite designed to do what no ground-based instrument ever could: measure the cosmic microwave background with precision across the entire sky. The satellite was called the Cosmic Background Explorer, and it carried 3 instruments, each built to answer a different question about the oldest light in the universe. But it was the first of those instruments that would produce one of the most remarkable measurements in the history of physics. The Far Infrared Absolute Spectrophotometer was led by a quiet, meticulous physicist named John Mather. He had been working toward this moment since his doctoral research in the early 1970s, when he first attempted to measure the spectrum of the cosmic microwave background from a high-altitude balloon. That early experiment had failed. The balloon payload was damaged, but the question had never left him. If the universe truly began in a hot, dense state, then the radiation left behind should carry a very specific spectral signature. It should be a blackbody. A blackbody spectrum is the thermal fingerprint of a system in perfect equilibrium. It is the radiation profile produced by an object that absorbs and re-emits energy with complete efficiency, and its shape depends on only one thing: temperature. The hot Big Bang model predicted that the cosmic microwave background should be the purest blackbody in nature, because the early universe was the most perfect thermal equilibrium that has ever existed. Every photon, every electron, every proton had been locked together in a state of such thorough energy exchange that the radiation should carry that signature with extraordinary fidelity, even after billions of years of cosmic expansion. Measuring this from the ground is extraordinarily difficult. The Earth's atmosphere absorbs and emits its own microwave and infrared radiation, contaminating the signal. Previous measurements had confirmed the cosmic microwave background was roughly consistent with a blackbody, but the error bars were large. No one had measured the full spectrum with the precision needed to test whether the match was truly exact. The Far Infrared Absolute Spectrophotometer changed that. The instrument used an external calibrator, a carefully engineered blackbody source cooled to the temperature of the cosmic microwave background itself, and compared the sky's signal against it with extraordinary sensitivity. The technique was elegant in principle, but punishing in execution. Every source of systematic error had to be identified and eliminated. Every component had to perform flawlessly in the cold vacuum of orbit. Mather and his team had spent more than a decade building, testing, and refining the instrument before it ever left the ground. The Cosmic Background Explorer reached orbit in November of 1989. Within minutes of the Far Infrared Absolute Spectrophotometer beginning its observations, the data began to take shape, and what it showed was breathtaking. The spectrum of the cosmic microwave background was a black body. Not approximately. Not within generous margins of error. It was a black body to a precision of better than 50 parts per million. The measured curve and the theoretical prediction lay on top of one another so perfectly that when plotted on a graph, the error bars were smaller than the thickness of the line itself. No natural source in the known universe produces a blackbody spectrum this clean. Nothing in any laboratory on Earth comes close. The cosmic microwave background is, by a significant margin, the most perfect thermal spectrum ever measured. John Mather presented the result at the American Astronomical Society meeting in January of 1990. He showed a single slide. The measured spectrum overlaid on the theoretical blackbody curve. The data points sat on the prediction so precisely that the audience could not distinguish one from the other. The room rose to its feet. Physicists do not, as a rule, give standing ovations. This was an exception. What they were looking at was not merely a confirmation of the Big Bang. It was proof that the early universe had been in a state of thermal equilibrium so complete, so flawless, that billions of years of cosmic evolution had not been able to disturb it. The temperature, 2.725 Kelvin, was now measured with a certainty that left no room for doubt. The implications were profound. A spectrum this perfect meant that the hot Big Bang model was not just plausible. It was, in the most rigorous spectral sense, confirmed. Any competing model of the universe's origin would now have to explain how such an immaculate black body could arise without a hot, dense beginning. None could. The steady-state model, already weakened by the original discovery of the cosmic microwave background, was now effectively ruled out by the sheer perfection of its spectrum. Mather would share the Nobel Prize in Physics in 2006 for this work. But the weight of the achievement is perhaps best captured by something simpler than a prize. In the entire observable universe, across billions of light years, across every star, every nebula, every galaxy, nothing radiates as perfectly as the afterglow of the beginning. The oldest light is also the purest. And it took a satellite, a decade of engineering, and a physicist who refused to let go of a question from his doctoral years to prove it. The spectrum was perfect, almost too perfect. A universe in flawless thermal equilibrium, radiating with a purity that nothing else in nature could match. But if the early universe had been truly uniform, if the primordial plasma had been perfectly smooth, without a single ripple or variation in density, then the cosmos we inhabit could never have existed. There would be no galaxies, no stars, no planets, no structure of any kind. Gravity needs something to work with. It needs a region, however slight, where matter is fractionally denser than its surroundings. Without that seed, gravitational collapse cannot begin. A perfectly smooth universe would remain perfectly smooth forever. An endless, featureless gas, cooling and thinning into oblivion. The cosmic microwave background had to contain imperfections, and finding them was the purpose of the Cosmic Background Explorer's second instrument. The differential microwave radiometer was led by George Smoot, a physicist at the Lawrence Berkeley National Laboratory, where John Mather's instrument had measured the overall spectrum of the cosmic microwave background. Smoot's was designed to do something different, to map tiny differences in temperature from one part of the sky to another. The challenge was immense. The cosmic microwave background is uniform to an extraordinary degree. Any fluctuations, if they existed, were expected to be vanishingly small. Variations of perhaps 1 part in 100,000, or roughly 18 millionths of a degree. Detecting a signal that faint against the noise of the instrument, the galaxy, and the Earth itself required years of careful observation and painstaking data analysis. In 1992, Smoot and his team announced what they had found. The cosmic microwave background was not perfectly uniform. It carried tiny temperature fluctuations, patches of sky that were fractionally warmer or cooler than the average, distributed across the entire observable sky in a pattern that was neither random nor regular, but somewhere in between. The amplitude was almost exactly what theorists had predicted. 1 part in 100,000, barely there, but real. Smoot described the moment with a phrase that would follow him for the rest of his career. He called it seeing the face of God. The language was dramatic, but the sentiment behind it was not exaggeration. What the differential microwave radiometer had revealed was the origin of everything. Those faint ripples in temperature corresponded to regions where the density of the primordial plasma was fractionally higher or lower than its surroundings. The slightly denser regions had marginally stronger gravitational pull. Over billions of years, that tiny advantage compounded. Matter fell inward, gas collected, stars ignited, galaxies formed, clusters assembled. The entire cosmic web, the vast filamentary structure of the observable universe, grew from seeds that were already present in the cosmic microwave background, imprinted when the universe was less than 400,000 years old. The connection reaches even deeper. The leading explanation for where those density fluctuations came from points not to some classical process in the early plasma, but to quantum mechanics. The theory of cosmic inflation, first proposed by Alan Guth in 1981 and developed further by Andrei Linde and others, holds that the universe underwent a brief period of extraordinarily rapid expansion in its earliest moments, a fraction of a second after the Big Bang. During this expansion, quantum fluctuations, tiny random variations in energy that exist at the subatomic scale, were stretched to cosmic sizes. What began as uncertainty at the smallest scales became the density variations that the differential microwave radiometer detected billions of years later, frozen into the cosmic microwave background like fingerprints pressed into cooling wax. This is one of the most extraordinary bridges in all of physics. The largest structures in the universe, galaxy clusters spanning hundreds of millions of light years, trace their origins to quantum events smaller than an atom. The cosmic microwave background is the record of that connection. It is the moment when the subatomic became the cosmic, written in variations of temperature so small that it took a satellite and years of analysis to read them. Andrei Sakharov had glimpsed part of this picture decades earlier. In 1965, working independently of the Western cosmological community, he predicted that the early universe should contain acoustic oscillations, pressure waves propagating through the hot plasma. His insight was ahead of its time, and it pointed towards something that the cosmic background explorer had only begun to reveal. The fluctuations in the cosmic microwave background were not random noise, they carried a pattern. And that pattern was the signature of sound. Not sound as we experience it, not vibrations in air, but sound in the physicist's sense, pressure waves propagating through a medium. In the first 380,000 years of the universe, the primordial plasma was that medium, and it was ringing. The physics is elegant and violent at the same time. In regions where the density of the plasma was slightly higher than average, gravity pulled matter inward, compressing it. But the photons trapped within the plasma resisted that compression. They exerted an outward radiation pressure, pushing back against gravity's pull. The result was oscillation, matter falling inward, radiation pushing it back out, matter falling inward again. A cosmic tug-of-war between gravity and light, playing out simultaneously in regions across the entire universe. These were baryon acoustic oscillations, and they propagated through the plasma at roughly half the speed of light. When recombination arrived and the universe became transparent, the oscillations froze. Whatever state each region was in at that precise moment, compressed, rarefied, or somewhere in between, was locked into the cosmic microwave background as a temperature variation. Compressed regions were slightly hotter. Rarefied regions were slightly cooler. The pattern of those frozen sound waves is still visible today, imprinted in the angular distribution of temperature fluctuations across the sky. The tool for reading this pattern is called the angular power spectrum. By measuring the sizes and amplitudes of temperature fluctuations at different angular scales, from the broadest features spanning many degrees down to fine detail at fractions of a degree, cosmologists can decompose the cosmic microwave background into a series of peaks and troughs. Each peak corresponds to a specific harmonic of the original sound waves, and each one encodes different physical information about the early universe. The first peak is the most important. It corresponds to the fundamental mode of oscillation, the largest regions that had time to complete exactly one full compression before recombination froze them in place. Its angular position on the sky, at approximately 1 degree, is extraordinarily sensitive to the geometry of the universe. If the universe were curved like the surface of a sphere, that peak would appear at a larger angle. If it were curved like a saddle, a smaller angle. The fact that it appears at almost exactly 1 degree tells us that the universe is spatially flat, that parallel lines extended across billions of light years remain parallel. Space, on the largest scales, has no curvature. This result was confirmed decisively by the balloon observations of millimetric extragalactic radiation and geophysics experiments led by Paolo de Bernardis at the University of Rome and Andrew Lang at the California Institute of Technology. Their instrument flew on a high-altitude balloon over Antarctica in 1998, mapping a small patch of the cosmic microwave background with enough resolution to pinpoint the first acoustic peak. The results, published in 2000, provided the first strong observational evidence that the geometry of the universe is flat, a finding that would be confirmed and refined by every subsequent experiment. The higher peaks carry their own secrets. The ratio between the heights of the first and second peaks reveals the density of ordinary baryonic matter in the universe, the protons, neutrons, and electrons that make up stars, planets, and everything we can see. The ratio between the second and third peaks constrains the density of dark matter, matter that exerts gravitational influence but does not interact with light. By reading the harmonic series of the cosmic microwave background, cosmologists can weigh the ingredients of the universe without ever touching them. There is something haunting about this. The sound waves that produce these peaks have not existed for nearly 14 billion years. They froze at recombination and have been silent ever since. But their signature persists, not just in the cosmic microwave background, but in the distribution of galaxies themselves. The sound horizon, the maximum distance a pressure wave could travel before recombination, left a characteristic imprint at a scale of roughly 150 megaparsecs. That scale is still visible today in the clustering of galaxies, a faint echo of a sound that rang through the universe before any star had ever formed. Joseph Silk predicted in 1968 that the smallest scale oscillations would not survive. Photons diffusing through the plasma before recombination would smooth out fluctuations below a certain size, erasing the finest details. This process, now called silk damping, sets a natural limit on how much detail the cosmic microwave background can reveal. It is the resolution limit of the oldest light, a boundary not of our instruments, but of the physics itself. The Cosmic Background Explorer had revealed two foundational truths. The spectrum was a perfect black body. The temperature was not perfectly uniform, but its instruments, powerful as they were, could only see so much. The differential microwave radiometer had an angular resolution of roughly 7 degrees, meaning that any detail in the cosmic microwave background smaller than about 14 times the width of the full moon was invisible to it. The broad strokes were there. The fine detail was not. To read the harmonic series of the acoustic peaks, to extract the precise numbers that would tell us the age, geometry, and composition of the universe, cosmologists needed sharper eyes. Those eyes arrived in 2001, when NASA launched the Wilkinson Microwave Anisotropy Probe, named after David Todd Wilkinson, the Princeton cosmologist who had been among the first to pursue the cosmic microwave background experimentally, and who died shortly before the satellite began its observations. The mission was led by Charles Bennett at Johns Hopkins University, with key theoretical contributions from David Spergel and instrumental design by Lyman Page, both at Princeton. The probe was placed at the Sun-Earth L2 Lagrange point, a gravitationally stable location roughly 1.5 million kilometres from Earth, where the Sun, Earth, and Moon are all on the same side of the sky, and thermal interference is minimised. It was, by design, one of the coldest and quietest places a telescope could sit. The WMAP results transformed cosmology. Over 9 years of observation, the satellite produced a full sky map of the cosmic microwave background at an angular resolution of roughly 12 arc minutes, more than 30 times sharper than the Cosmic Background Explorer. For the first time, the acoustic peaks in the power spectrum could be measured with precision. The first peak confirmed spatial flatness. The higher peaks revealed the relative proportions of baryonic matter and dark matter. The overall pattern, when fitted to the standard lambda-CDM cosmological model, yielded a set of numbers that defined the universe with startling specificity. The age of the universe, 13.77 billion years. The proportion of baryonic matter, roughly 4.6%. The proportion of dark matter, roughly 23%. The proportion of dark energy, roughly 72%. The Hubble constant, approximately 71 kilometers per second per megaparsec. These were not rough estimates. They were precision measurements derived from light that had been travelling since the universe was 380,000 years old. WMAP had inaugurated what cosmologists began calling the era of precision cosmology, the point at which the fundamental parameters of the universe moved from educated guesses to measured values with meaningful error bars. But precision is a ladder, and the next rung was already being built. ESA's Planck satellite launched in 2009, carrying instruments that surpassed WMAP in every dimension. 9 frequency channels spanning 30 to 857 GHz gave Planck the ability to observe the cosmic microwave background across a far broader range of wavelengths, allowing it to separate the true cosmological signal from foreground contamination. The synchrotron radiation, free emission, and thermal dust emission produced by our own galaxy, all of which overlay the ancient light and must be carefully stripped away before the cosmic microwave background itself can be read. The angular resolution reached 5 arc minutes at the highest frequencies, more than twice as sharp as WMAP. The sensitivity was an order of magnitude better. The project scientist Jan Tauber oversaw the mission from ESA's European Space Research and Technology Centre. The satellite carried 2 primary instruments, the high-frequency instruments, led by Jean-Loup Puget at the Institut d'Astrophysique Spatiale in Orsay, and the low-frequency instrument, led by Nazareno Mandolesi in Bologna. Together, they produced the most detailed all-sky map of the cosmic microwave background ever made, an image of the universe at 380,000 years old, rendered in temperature variation so fine that individual features spanning a fraction of a degree could be resolved. Planck's measurements refined every number WMAP had produced. The age of the universe shifted slightly to 13.799 billion years, with an uncertainty of just 21 million years, a margin of error of roughly 0.15% on a measurement spanning the entire history of the cosmos. the composition settled into sharper focus. Approximately 68.3% dark energy, 26.8% dark matter, 4.9% baryonic matter. The Hubble constant, as measured from the cosmic microwave background, came in at 67.4 kilometers per second per megaparsec. These numbers are deceptively simple. Behind each one lies a story about what the universe is made of, and how little of it we truly understand. Start with what we know. The 4.9% that is baryonic matter accounts for everything the human senses can detect, and everything human instruments can directly observe. Every star in every galaxy, every planet, every moon, every asteroid, every ocean, every mountain, every molecule of air, every atom in every living body. All of it, the totality of the visible, tangible, luminous universe, represents less than 1 part in 20 of the total energy content of the cosmos. The cosmic microwave background revealed this not through guesswork, but through the precise ratios of its acoustic peaks, each one a weighing scale for a different ingredient. Dark matter, at 26.8%, is the next largest fraction. It does not emit light. It does not absorb light. It does not scatter light. It has never been directly detected by any instrument. Yet its presence is written unmistakably into the cosmic microwave background. The relative heights of the odd-numbered and even-numbered acoustic peaks are sensitive to the ratio of baryonic matter to dark matter. If dark matter did not exist, the peaks would look fundamentally different. The pattern would be wrong. The cosmic microwave background does not merely suggest that dark matter is real. It demands it. And it tells us precisely how much of it there is, to a precision that no galaxy rotation curve or gravitational lensing measurement can match. Then there is dark energy. At 68.3%, it is the dominant component of the universe, and it is the least understood. The cosmic microwave background constrains dark energy not through its direct imprint on the ancient light, but through its effect on the geometry and expansion history of the universe. The position of the first acoustic peak, that 1 degree angular scale that signals spatial flatness, requires the total energy density of the universe to equal the critical density. Baryonic matter and dark matter together account for roughly 31%. The remainder must be something else. That something else, consistent with a cosmological constant in Einstein's field equations, is what drives the accelerating expansion of the universe discovered independently through observations of distant supernovae. The cosmic microwave background does not explain what dark energy is, but it measures how much of it there is with a certainty that leaves very little room for alternatives. What the oldest light tells us then is this: the universe is precisely 13.8 billion years old. It is geometrically flat, and it is made almost entirely of things we cannot see, cannot touch, and do not understand. 95% of everything that exists is invisible. The cosmic microwave background delivered this verdict not through a single observation, but through the accumulated precision of 3 satellite missions spanning 2 decades, each one building on the last, each one sharpening the same ancient signal into a clearer and more humbling picture of reality. Light can do more than carry temperature. It can carry direction. When a photon scatters off an electron, the angle at which it scatters determines whether it emerges with a preferential orientation, a subtle alignment in the direction its electric field oscillates. This property is called polarization, and it is written into the cosmic microwave background alongside the temperature fluctuations, fainter but no less important. If the temperature map is a photograph of the early universe, the polarization map is its hidden watermark, a second layer of information, encoded in the orientation of light rather than its intensity, carrying messages that the temperature alone cannot deliver. The polarization of the cosmic microwave background was first detected in 2002 by the Degree Angular Scale Interferometer, a ground-based experiment operating at the South Pole. What it found was a specific pattern known as E-mode polarization, a curl-free arrangement generated by the same density fluctuations that produced the temperature anisotropies. E-modes were expected. They were predicted by the standard cosmological model, and their detection confirmed that the physics of the photon baryon plasma was understood in fine detail. WMAP and Planck subsequently mapped the E-mode signal across the full sky, tightening the constraints on cosmological parameters even further. But there is a second type of polarization pattern, one that carries far more dramatic implications. B-mode polarization has a swirling, divergence-free structure that cannot be produced by ordinary density fluctuations. Only two known sources can generate it. The first is gravitational lensing, the bending of cosmic microwave background light by the large-scale structure of the universe as it travels toward us across billions of years. This lensing B-mode signal was detected by the South Pole Telescope in 2013 and has since been measured by multiple experiments. It is real, it is well understood, and it tells us about the distribution of matter between us and the surface of last scattering. The second source is far more elusive and far more consequential. If cosmic inflation occurred, if the universe truly underwent a brief, violent burst of exponential expansion in its earliest moments, then that expansion should have generated gravitational waves. Not the gravitational waves produced by merging black holes, but primordial gravitational waves, ripples in the fabric of space-time itself, stretching across the entire universe. These waves would have left a distinctive B-mode signature in the cosmic microwave background, a swirling pattern imprinted at the moment of last scattering that no other known process could mimic. Detecting this signal would be direct evidence that inflation happened, and it would reveal the energy scale at which it occurred, a window into physics at energies far beyond the reach of any particle accelerator ever built or conceivable. In March of 2014, the BICEP-2 collaboration announced that they had found it. The experiment, located at the Amundsen-Scott South Pole Station, had been designed specifically to search for primordial B-modes. The team reported a signal at a level that was unexpectedly strong, a tensor-to-scalar ratio that, if confirmed, would have been the first direct observational evidence of cosmic inflation. The announcement made global headlines. Physicists wept on camera. The result was hailed as one of the most important discoveries in modern cosmology. Then the doubts began. The cosmic microwave background is not the only thing between the BICEP-2 telescope and the edge of the observable universe. Our own galaxy is filled with dust, tiny grains of silicate and carbon that emit their own polarized radiation in the microwave and sub-millimeter bands. If that galactic dust happened to produce a polarization pattern that mimicked the primordial B-mode signal, the entire detection could be a false alarm. The BICEP-2 team had estimated the dust contribution and judged it to be small, but they had relied on preliminary data and the full picture was not yet available. It arrived the following year. The Planck satellite, with its broad frequency coverage, produced the first comprehensive map of polarized dust emission across the sky. A joint analysis by the BICEP-2, Keck Array, and Planck collaborations, published in 2015, delivered the verdict. The signal that had electrified the world could not be distinguished from galactic dust contamination. The primordial B-mode detection was not confirmed. The excitement had been premature. The episode was not a failure of science. It was science working exactly as it should. A bold claim subjected to rigorous scrutiny and found wanting. But it underscored just how difficult the search for primordial gravitational waves truly is. The signal, if it exists, is buried beneath foreground contamination that must be modelled and removed with extraordinary precision. Next generation experiments: the Simons Observatory in the Atacama Desert, Cosmic Microwave Background Stage 4 with its network of ground-based telescopes, and JAXA's planned Lightbird satellite designed to observe from space, are being built specifically to reach the sensitivity required either to detect primordial B modes or to rule them out at the levels predicted by many inflationary models. The answer is not yet in hand, but the pursuit continues, and the stakes remain as high as they have ever been. The search for B modes is not the only unresolved question the cosmic microwave background has opened. Some of its deepest puzzles are not about what we have failed to detect, but about what the data already shows. Features and tensions that the standard model cannot comfortably explain. The most prominent is the Hubble tension. The Planck satellite, using the cosmic microwave background to infer the current expansion rate of the universe, measures the Hubble constant at approximately 67.4 kilometers per second per megaparsec. This is a prediction. The value the expansion rate should have today, if the lambda c dm model is correct and the universe has evolved according to its standard parameters since recombination. But when astronomers measure the Hubble constant directly, using the local distance ladder, Cepheid variable stars calibrated against supernovae in nearby galaxies, they consistently find a higher value, closer to 73 kilometers per second per megaparsec. Adam Rees and the Shoes team have refined this local measurement over more than a decade, and the discrepancy now exceeds 5 sigma. In statistical terms, this is well beyond the threshold at which a result can be dismissed as coincidence. Something is wrong. Either there is an unidentified systematic error in one of the measurements, or the standard cosmological model is missing something. A new particle, a new interaction, a change in the behaviour of dark energy, or something else entirely that no one has yet imagined. Then there are the anomalies in the cosmic microwave background itself. The cold spot, an unusually cold region in the southern sky, roughly 10 degrees across, far larger and colder than the standard model predicts, has resisted explanation since it was first identified in WMAP data. One hypothesis, proposed by Istvan Sapudi and colleagues, attributes it to the Eridanus supervoid, an enormous underdensity in the cosmic web along the line of sight. But whether a void of the required size could produce a temperature deficit this large remains debated. Other proposals reach further, including the speculative suggestion that the cold spot could be a scar left by a collision with another universe in a multiverse framework. The hemispherical power asymmetry is subtler but equally stubborn. The amplitude of temperature fluctuations is slightly but measurably different between the two halves of the sky. This should not happen. The standard cosmological model assumes that the universe is statistically isotropic, that its properties, on average, are the same in every direction. The asymmetry was flagged by both WMAP and Planck, and no convincing explanation has emerged. Related to this is the so-called axis of evil, an unexpected alignment of the largest scale fluctuations in the cosmic microwave background with the plane of the solar system. Whether this is a genuine cosmological signal, an artifact of foreground contamination, or a statistical fluke remains an open question. And beyond what current instruments can see, there are signals waiting to be found. Theorists, including Rashid Sunyaev and Yakov Zeldovich, predicted decades ago that specific types of energy injection in the early universe, from the annihilation of exotic particles, the dissipation of primordial sound waves, and even the process of recombination itself, should produce tiny distortions in the cosmic microwave background's otherwise perfect blackbody spectrum. These spectral distortions have never been detected. The Cosmic Background Explorer's far-infrared absolute spectrophotometer was not sensitive enough to see them, but proposed future missions, including a concept called Pixie, have been designed specifically to reach the sensitivity required. If they fly, they would open an entirely new window onto the early universe, a window that the cosmic microwave background has been holding open for nearly 14 billion years, waiting for instruments precise enough to look through it. There is a tendency, when talking about the cosmic microwave background, to speak of it in the past tense, to treat it as a relic, something that happened long ago in a universe that no longer exists. And in one sense, that is true. The light was released nearly 14 billion years ago, from a plasma that cooled into atoms before the first star had ever burned. The universe it came from is gone, but the light is not. It is here, right now, in this room, in every room. Roughly 411 photons of the cosmic microwave background occupy every cubic centimetre of space in the observable universe. They pass through walls. They pass through skin. They pass through the spaces between atoms. They are moving through you at this moment, as they have been for every moment of your life, as they were for every moment of the Earth's existence, as they will be for as long as anything exists to be passed through. The oldest light in the universe is not distant. It is intimate. It is closer to you than the air in your lungs. Every radio telescope ever built sits inside it. Every satellite launched into orbit is bathed in it. When engineers first designed sensitive microwave receivers, they found a faint noise floor they could not eliminate. And that noise floor was the cosmic microwave background, pressing gently against every detector, an irreducible hum from the beginning of time. As the universe continues to expand, this light continues to cool. Its wavelengths stretch. Its temperature drops. It has already faded from the searing glow of 3000 Kelvin at recombination to the faint microwave whisper of 2.725 Kelvin today, and it will go on fading. In the deep future, it will shift from microwaves into radio waves, its wavelengths growing longer and longer, its energy diminishing with each passing epoch. In a universe dominated by dark energy, where the expansion of space accelerates without end, there will come a time, unimaginably far from now, when the cosmic microwave background has redshifted beyond the sensitivity of any conceivable instrument. The oldest light will not have been destroyed. It will simply have become too faint, too stretched, too diluted by the expansion of space to ever be detected again. Lawrence Krauss and others have explored what this means for the far future of knowledge itself. A civilization arising in that distant era, trillions of years from now, long after the last stars have died, would find no cosmic microwave background, no remnant radiation, no evidence that the universe ever began in a hot, dense state. They would observe their own galaxy, isolated by the expansion of space from every other galaxy in the observable universe, and they might reasonably conclude that they were alone in a static, eternal cosmos. The evidence of the Big Bang would have been erased not by destruction, but by distance. the universe would have outgrown its own origin story, we live in a window. A brief, improbable window in the history of the cosmos during which the evidence of the beginning is still detectable, still readable, still passing through us at every moment. The cosmic microwave background is not merely a scientific measurement. It is a message from a universe that was once a wall of incandescent plasma, written in the only language it had, thermal radiation, and sent in every direction at once to anyone or anything that might one day develop the instruments and the curiosity to receive it. Penzias and Wilson heard it as a hiss they could not explain. The cosmic background explorer saw it as a perfect curve and a sky of tiny imperfections. W. Mapp and Planck read it as the age, the shape, and the composition of everything. And still, after decades of observation, after 3 generations of satellites and countless ground-based experiments, it has not finished speaking. There are messages in its polarization we have not yet decoded. There are distortions in its spectrum we have not yet detected. There are anomalies in its patterns we do not yet understand. The oldest light is patient. It has been travelling for nearly 14 billion years. It is in no hurry. And it is still here, still everywhere, still waiting, still carrying the memory of the moment the universe first opened its eyes.